back to Maths with Mr. Hanna. Okay, in the previous video, we were learning to do matrix multiplication, where we were told a matrix A, and we timed that matrix with another matrix B, and we found an answer, assuming that the dimensions are right, of A and B, of course. We found an answer which came out to be a matrix X. Okay, in this video, we're going to be solving matrix equations. Now, what we had previously was more of an expression. We knew A times B, and we were trying to find this X. This X was the thing we didn't know. Now, it's going to be a bit different, a different situation. We've got a matrix A, and we're going to times by a matrix X. So an unknown matrix gives us a matrix B, a matrix we do know. So the difference is, in the previous video, we didn't know what our answer was going to be. In this video, we don't know what this matrix here is, matrix X, that we need to find out so that it gives us the answer, matrix B. Okay, now the first thing to realize is this is not so different from just any other sort of algebraic sort of equation. So imagine if we had a situation that wasn't matrices, it was just regular old sort of numbers. So imagine if we had AX equals B. Okay. Now let's now to find sort of the answer to this, how we would do it is we would know that if we multiplied both sides by whatever the inverse of A is, so if we found the inverse of A, multiplied that by X, and we also multiplied the inverse of A, I've kind of stuffed that up, excuse me. If we find the inverse of A, multiply that by both sides, so we've got the inverse of A multiplied by A times X on this side, and here we would have the inverse of A multiplied by B. So to both sides, we've done a multiplier by the inverse of A. Now the reason we do that is because we know that the inverse of A times by A, well, what is an inverse? The inverse is something that undoes something else. So these two, the inverse of A and A, they undo each other. In other words, together they equal 1. So over here we've got 1 times X, which is obviously just X, and over here we've got the inverse of A times B. Now that may all seem very confusing, so let me just do it again, but this time instead of using just algebra, A and B here for my parameters, I'm going to use actual numbers to make it a bit more obvious. So imagine we had 5x equals, let's say 30. Okay, 5x equals 30. Now to solve this, what we do is we find the inverse of 5. Now the inverse of 5 is a fifth. Now so the inverse of 5 is a fifth. The reason is because a fifth times 5 equals 1. So a fifth is the inverse of 5. And you know from your index laws, you can actually write this. You can write 1/5 is actually the same as just 5 to the power minus 1. And that's where this index looking thing comes from. So I'm going to multiply this by the inverse and multiply that by 5 and by x equals the inverse of 5. Oops, the inverse of 5 multiplied by 30. So here the inverse of 5 cancels with 5, leaving us just with x on this side, and 5 to the negative 1 times 30 on this side, and of course 5 to the negative 1 is a fifth, and 30, so 30 times a fifth is 30 divided by a fifth, and of course the answer is therefore 6. 30 divided by 5 is 6. Okay, so that may, so hopefully you follow this. It's actually what you've been doing for years now in maths, but done in a more precise way than you've probably done in the past. And it's actually going to be the exact same way that we're going to solve our matrix equations. So what we're going to do, we're going to find an inverse. So we're going to multiply both sides by the inverse of A. So we'll multiply both sides by the inverse of A. And instead of the inverse of A multiplying by A, that doesn't equal 1 anymore. That now equals, so the inverse of A times by A actually equals an identity matrix. So you remember from our previous video, an identity matrix has 1s down the diagonals, but 0s everywhere else. So if A here, if A is a 3 by 3 matrix, then you'll get this identity matrix that's a 3 by 3 as well. If A is 2 by 2, then you'll get an identity matrix that's only a 2 by 2, only that big, and so on and so forth. So this bit here equals an identity matrix, and then the rest is the same. Now the reason identity matrices are cool or are good is the identity matrix times a matrix that's the same size as it, or that's able to be multiplied by it. So the identity matrix times anything, say times the matrix A, equals the matrix A again. It does nothing. It's kind of like the matrix version of the number 1. Or the identity matrix times B equals B. Identity matrix times X equals X. Instead of the pattern here, multiplying by the identity matrix does nothing, just gives the same thing back. So the identity matrix times X over here, that's just X. And so X is the inverse of A multiplied by B. And that will find the answer that we're looking for. This X was the answer we're looking for. So let's sort of corner that off. Okay, so what we're trying to do, we're going to be given an equation that looks like this, a matrix times X equals B. And what we're essentially going to do to find X, so you can kind of think about this working out in your mind, but to find X, you've got to find the inverse of A and multiply that by B. So here, it's now no harder than what we were doing last video, because we're just now multiplying two matrices together. So what we've got to do is, so steps, we've got to find the inverse to A, because here we've got where we know A, we don't know its inverse. So we've got to find the inverse of A, that's step 1, and step 2 is just do the matrix multiplication of the inverse multiplied by our answer matrix B. So those are the things we're going to be actually doing. Okay, so all of that, everything we've covered is just a big sort of preamble, sort of an intro of what we're actually going to do. So now let me explain a little bit about finding the inverse, if you like. Okay, so time to find the inverse. Okay, finding the inverse of a matrix. Now, all that's covered in this course is 2 by 2 matrices in terms of finding inverses, which is handy because it gets a lot more difficult a lot quickly when you look at larger order matrices and finding their inverses. So first off, the whole point of an inverse is that an inverse matrix multiplied by sort of the original matrix gives you an identity matrix. Now this sort of only works when everything is a square matrix, because you remember that identity matrices must be square. So here our matrix A must be square. So I need to say where matrix A is a square matrix. Okay, so that is important, that a matrix A is a square matrix. Okay, let's do this. First off, I'll try and do it sort of the long way. I'll explain how it is that we get the answer. So with this in mind, there's going to be a And remembering that on this course we're only dealing with matrices of order. So let's have our order of our matrix A is going to be a 2 by 2 matrix. So let's say that, well, our inverse matrix, so we're going to have our inverse matrix here, we're going to multiply that by our original matrix A. And that will have to equal our identity matrix. So let's sort of put that out in this way. So this will be our inverse matrix, and it'll be made up of 4 things, and then we're going to be multiplying that by our matrix A is this one, and let's make it have just general elements. So let's say this is element A, then we will have element B here, element C, element D, and it must equal an identity matrix, so it must equal something that looks like that. Okay, so basically we have, let's say here we have V, W, X, and Y. And our job is to find out what V, W, X, and Y are actually going to be. So assume we're told A, B, C, and D, we need to find out V, W, X, and Y. So our aim here is to find a formula so you don't have to do all this effort that I'm about to do right now. You don't want to have to do that every time. So first off, we're multiplying 2 square matrices. So to get this number 1, that is the first row multiplied by the first column. So we have V times A plus W times C has to equal 1. Has to equal 1 here. Now to get this 0 here, it's going to be the first row times the second column. So that's V times B plus W times D, and that has to equal 0 because that's 0. Now to find our third spot, this other 0, we've now got the second row multiplied by the first column, so that's X times A plus X times C equals 0. And our final spot is going to be our second row times our second column, XB plus YD. Whoops, by the way, this earlier one I stuffed up clearly. That's actually YC earlier. Okay, sorry about that. YD equals 1. Okay, so now what we have is 4 equations and 4 unknowns. So we're able to use our simultaneous equations on this to find out what our answers to V, W, X, and Y are going to be. So you're able to do this sort of in any way you like. You can use substitution over and over again, lots and lots of times, and that will work. But what I'm going to do for you is, because I don't think anyone's got the patience to actually try this, so feel free to try this with pen and paper if you like. I will probably give you a Mars bar if you show me you're working out and bring that to class. But what I'm going to do is I'm just going to use our CAS calculator to solve this system of equations. So I'll get it out. Here's our CAS calculator, new calculator page. Okay, so we're going to be using a system of equations here. All right, get rid of that. So we're doing some algebra, menu, algebra, solve a system of equations. We have 4 equations. Variables, let's call them the same thing. So let's say we've got V, W, X, and Y. Okay. Okay, next we'll fill in these 4 equations here. Okay, so here we go. I've just put those in. Please note that I had to clear all of my variables before I did this. Otherwise, these A's and B's would be other things I'd previously saved in my calculator. So here we go with a bit of luck. If I press enter, here are all of my different values. It says V is D on AD minus BC. W is minus B on AD minus b dot c, and x is this, and if I keep going across, and y is, whoa, there we go. So let me just try and write those out a bit more clearly. So v, oh, that's interesting. Okay, now at this current point, there's no way to actually save these in your calculator as variables. Like if you want to look for what x equals, you can see it written right here. But if you just type x, it just returns x because it's not been saved into memory. The only way to actually save it is to, if you go back up, you can highlight things like that bit and go Control C for copy, and then back down you can use your Control V for paste if you want. So there, that is, this one's going to be Y, isn't it? Whoops, didn't mean that space. So there we go. So that one is, that one's Y there. And we've got the others as well. So if you want, you can store these as variables by using a store. So that one is Y. There we go. And let me just store the others for you really quickly. Okay, so I've used copy and paste to save these all as variables, and now I can list them using my curly brackets. I can list them all at once. I want V, W, X, and Y to all be listed together. So I've used curly brackets to show that there's a list of numbers, or a set, if you like. So here I've got my V up in this position will be this number. I've got my W next, X next, and then Y last. Now hopefully you notice that the denominator in every single case is exactly the same. The denominator is AD minus BC. AD minus BC, AD minus BC, AD minus BC. It's the case for every single one. So what you can actually do is take that out as a factor to clear it up. And then all you've got to remember is D minus B minus C, A. So let me show you what our solution looks like. So our original matrix, this one here, which is our inverse matrix of A, looks like this. Well, the first one was D, then we had minus B, and minus C, and A. And there was a factor, so the factor really should be brought out the front, I suppose, but I've left no room, so I'm going to put it at the back, which was the AD minus BC. AD minus BC as a factor. So this factor is being multiplied by each one of those. So this is, we now have a way, if this is our original matrix, A, B, C, D, then our inverse matrix is this. Okay, so this is like a shortcut that you can use over and over again. Yeah. Now, this factor out the front here, we give it a bit of a name. In particular, we call this bottom bit, we give that a name really. We call that the determinant. Okay, so we call that the determinant, or the determinant of A, if you like. And we write it as det A for determinant of A, or sometimes we write it with a modulus sign. So that also means the determinant of A, if you like, but we're mostly going to be using det A, if you like. Now, the reason the determinant is something important is because, as you well know, you can't divide something by 0. So the determinant cannot be 0. Otherwise, there is no inverse. So, so we can say an inverse only exists. Only exists if the determinant of A, or an inverse, A negative, only exists if the determinant of A does not equal 0. It's not allowed to equal 0. So let's do an example, I think. So let's go away. Let's write out what we know. So we know that if A equals A, B, C, D, then the determinant, the inverse of A, that's a negative sign, equals 1 divided by the determinant, A, D minus B, C, multiplied by our D minus B minus C, A. Okay, so that's sort of what we know so far. So here's an example. Find the inverse of, say, the matrix F equals 3, 1, 6, 0. Okay, find the inverse of F equals 3, 1, 6, 0. Well, first let's find the determinant. Determinant of F equals AD minus BC, of course, it's written there. So A times D, that's 6 times 0, minus B times C, 1 times 6, equals 6 times 0 is 0, minus 6 times 1 is 6, so that's minus 6. The determinant of F equals minus 6. Because this minus 6 is not 0, the inverse does exist. Okay, the inverse, and this time it'll be the inverse F minus 1, does exist. Okay, so it does exist. That's excellent. Now, our determinant F is minus 6, so now we're ready to just actually write our inverse. Well, it equals 1 over our determinant, so it equals 1 over minus 6, minus 1/6, multiplied by, now we've got in this position D, so that's 0. In the next position, we have minus B, so minus 1. This position we have minus C, so that will be minus 6. And in the final position, we have A, 3. So you can write it like this, or if you want to, you might want to put this this bit out the front into the bracket. So this, by the way, what we've done now is perfectly good. And if we wanted to, we could write it again, but putting this inside. So 0 times negative a sixth is 0, minus 1 times negative a sixth is a sixth, minus a sixth times negative 6 is 1, minus a sixth times 3 is negative a half. Okay, so these two things here, they are equivalent. So there's an equal sign to show that they're equivalent. So that is also a perfectly good answer as well for our inverse of F. Okay, now let's extend this example. Okay, so if we had a question that was, let's say, F times matrix X equals B, where now F can be our matrix that we had before, but let's say that our X matrix is X, X, Y. So we don't know those things, and that means because F is a 2 by 2 and we're multiplying by a 2 by 1, we're going to get a 2 by 1 as a result. So our result B is going to be a 2 by 1 as well. So it's going to be, let's just make something up. Let's have 6 and 10 will be the answer. So let's write this again. Our function of our matrix F times X equals B. In other words, F is this matrix, 3, 6, 1, 0. multiplied by x, xy equals b. 6, 10. There we go. Now, to solve this, we've got f times x equals b. To solve it, we're first going to multiply both sides by the inverse of f. As we've already seen before. So these ones will form the identity matrix. X equals. The identity matrix multiplied by any other matrix is the other matrix. So we've just got x equals f minus 1, b. So now to find our answer, all we need to do is the inverse of f times b. So here's our inverse of f down here. So x will equal our inverse of f, 0, 6, 1 minus a half. Multiply that by our matrix b, which of course is 6, 10. So, and we know our answer is going to be xy, so it's going to be looking like this. So in our first position, this is our A11, so we've got 0 times 6 is 0. Now plus a sixth times 10. 10 on 6. And in our second position, we've got 1 times 6 plus minus a half times 10. So that would be minus 5. So our overall answer, 0 plus 10 sixths is 5 thirds, because that's just the same as 10 sixths, and 6 minus 5 is 1. So we can say, therefore, x is, or if it's xy if you like, is 5 thirds and 1. There we go, and we have finished that question. Now, okay, so there's a big example for you. One other thing to note is we might be thinking, when would we ever be doing a matrix equation? When would they come up? When would we create one? When would we even want to? And the answer is that it's actually just a quicker, more powerful way of doing simultaneous equations. So have a look at this setup that we've got here. This 3, 1, 6, 0 times x, y equals 6, 10. Okay, I'm going to write some equations that actually are the same as this. So imagine I'm just doing the matrix multiplication, the matrix multiplication of this. I'm going to write down it as simultaneous equations. So first off, this 6 must equal 3 times x, must be 3x, 3 times x times 1y plus y, and that is what would go here, 6. And next up, to go in this position, it will be the second row times first column, so 6 times x, 6x, plus 0 y's, and that is going here, which is 10. So what this is actually simultaneous equations. Okay, so matrix equations are just a way of doing simultaneous equations, but they're a much more powerful way. And actually, if our system's made up of lots and lots of equations, they're actually much quicker and easier. Even though they don't look it right now, but that's only because you're just learning this stuff. They're quicker and easier, especially if you are a computer. There you are. Okay. And so that's why they're used so often. Okay, I think that is plenty. Actually, one last thing is you can actually find these inverses using your calculator as well. So let's create a matrix. Let's just do the same example that we done actually to see if we were correct. So matrix 3 1 6 0, and we're going to store that into A. Oh no, we'll store it into F. Might as well stay consistent with our example. Now to find the inverse, I'm just finding F to the power of -1 for the inverse, and there we go. It gives us our inverse, which is exactly the same as what we had found, which is perfect. So you can find the inverses like this and solve matrix equations very quickly using a calculator. Alright, that's all of the content in this video, but I realize that there's some people that are going to find this a little bit difficult, so I'm going to add one extra example right now. So if you feel like you understand, you might want to just get some practice. Otherwise, stick around for another 5 minutes and I'll do another example. Alright, so here's example 2. We're asked to solve this matrix equation here. And I've also written our key piece of information over here. So first, let's give this little matrix a name just so we can keep track of it. Let's call it a matrix, just pick our favorite, let's call it matrix D. Let's call this one X. And let's just call this one E. Doesn't really matter, just so we can keep track of things. So first off, I'm going to find the determinant of matrix D. Okay, determinant is, of course, given over here, AD minus BC. So in this case, it's 2 times 6 minus 1 times 5, which is 12 minus 5, which equals 7. So inverse exists. So the inverse exists. That's excellent news. So what we're going to do, we know that X is actually equal to the inverse of D multiplied by matrix E. Okay, so now let's find the inverse of D. D inverse, well, it equals 1 over our determinant, 1 over 7, multiplied by D goes in this spot, so 6. A in the other diagonal, so 2. That's flipped over, and the other ones stay where they are, but they're negative. Negative 1, negative 5. There we go. Now we're ready to do our matrix multiplication. So we know that X is going to be our D inverse times E. So D inverse is 1 over 7 multiplied by 6 minus 1 minus 5, 2. Multiply that by 3, 1. Okay. So due to the order, this first one is of course 2 by 2, 2 by 2. This second one is a 2 by 1. So the order of the result is going to be a 2 by 1. 2 by 1. Okay. First position is given by first row, first column. Of course, the factor of a 7th is still going to be there, so don't forget about that. 6 by 3, 18, plus minus 1 times 1. And down here we've got second row by first column, minus 5 times 3, minus 15, plus 2 times 1. So that equals our 1/7 that we won't forget about. 18 minus 1 is 17, and minus 15 plus 2, minus 13. And there is our answer. Let's quickly, if we want to, we can quickly check this using our CAS, which I'll do now. Okay, so here we go. Let's create a matrix. Yep, it's going to be 2 by 2. Okay, so our original one's 2, 1, 5, 6. 2, 1, 5, 6. And we will call that our matrix D, we called it. There we go. Now we need to name our matrix E. So let's create one of those. Now here's a shortcut one that you can see, just a column one there. So 3, 1, and we call that E. Matrix E. There we go. Now we wanted to find the inverse of D, so let's find that. The inverse of D. There's the inverse of D. Notice everything is over a seventh there. So now to find our final answer, we did the inverse of D times our matrix E. So let's do that. Now, inverse of D multiplied by matrix E. There we go, 17 on 7 and negative 13 on 7. Exactly the answer that we had obtained by hand. There we go. Hopefully that example has made things very clear for you. Best of luck, and I'll see you in class.